Uh, Hello everyone, thanks for being here. I'm Farzamnik and I'm a second year PhD student doing my PhD thesis on the title of Statistical Learning Tools for Turbulent Flow Control, which is guided by Andra from our department and also Vanessa Guerrero from Department of Statistics. And I had the chance to be in close collaboration with other colleagues, Stefano, again in our department, and some other ones in Berlin, Paris, and also Shenzhen, China. Well, let's start our journey talking a bit about motivations. Fluid dynamics has been studied for centuries, actually, and exploiting the capabilities of computational machines, we were able to address lots of different problems in this field. But there is also a lot of things to do, especially regarding to some complex flows like turbulence ones, like jet streams. And we are fortunate that even in these complex flows, we are able to see some similar behavior, some similar patterns that in terms of the data science field, we can understand and study them with a special group of techniques called manifold learning. So the idea is to use these manifold learning tools to understand and unravel these features inside or flows. When we started to look at the previous works, this manifold learner, especially the nonlinear one, has been developed and identified in recent 2 decades in lots of different applications, especially in the image recognition cases, and also in the field of the fluid dynamic and applying it in the control system. We have plenty of literatures using different models and different methods like Galerkian models, and also the machine learning tools to develop the control systems. But surprisingly, we couldn't find enough, contribution and application of this nonlinear manifold learner into the study of the fluid dynamics. And also this works was just limited to some let's say simple flow cases. So we started to think to move forward and do this nonlinear manifold learner apply to some complicated cases. So we define our objectives as these questions that if we are able to actually build a model to use this manifold learning tools to understand better our flows and unravel some physical characteristic hidden inside our flow data. And if we use this tool to reconstruct the actual flow fields, which is the first phase of our work already done. And in the next phase, can we use this tool into the problem of developing the control system, and also more ambitiously moving toward to optimization and design problems of a whole aerospace system, or for example, wing design. So talking about the general picture of our tool, we can have these 3 main blocks. Later we added another 4th one, and I will talk about this later. And here you can see the first block. It is our snapshots. which we obtain from different, let's say, CFD simulation or even the experimental data. And it could be either the raw images or the output of some processing like PIVs. And we use these snapshots and we look at them, loosely speaking, as, let's say, images of the flow. And each image has lots of different pixels. For instance, for our cases, some 100,000 pixels. And in terms of statistical learning, we call these values in different pixels as the high dimensional. So imagine it something like 100,000 dimension space that we have different snapshots through the time. And the ultimate goal of this encoder part is to somehow translate this high dimensional space to one low dimensional space while preserving the main characteristic and preserving the distances between the different snapshots. And well, I'm not going to go to detail of these steps. And at the end of this blog in encoder, we are able to have some representation of our case in very good fashion in 2 and 3 dimensions that we can have some interpretation about the physical features. And on the other side, in the decoder part, we goes the other way, starting from the low dimensional space to reconstruct the manifold in high dimensional space and to reduce the error between the reconstructed and actual flows. Let's just focus on some interesting result that we have obtained. For instance, you can see in this nice manifold that we obtained by using our decoder, that even though that our method up to this point is completely data-driven and physical blinded, it is able to explain the whole picture, the whole evolution of the vortex shading, starting from the initial condition toward some, in this case, some limit cycles. And moreover, it is possible that these different dimensions that we have in low dimensional embedding space have some correlation between with some physical features. For example, for instance, here we are seeing the perfect correlation between the CD and CL with our third and eighth dimensions in low dimensional space. And we thought that maybe we had this interesting result because we implement our method into CFD without any noise or something like this. But when we try our method in some more complicated experimental data, we got more surprising results even. Here on the left side, we can see the manifold that we have obtained from our decoder and from our encoder. And on the other side, you can see the result of PhD, POD, the well-known technique in analyzing fluid dynamics. And here you can clearly see that our method is able to find some hidden features, some hidden characteristics that POD is completely failed to do. And by examining the snapshots in different clusters in our embedding space, we can relate each cluster to different regimes of this flow configuration. Well, moving toward the decoder part, which the main objective is reconstruction of the actual snapshot. We are pleased to have such a nice result in terms of reconstruction error. In almost all the cases, we outperform the POD, reconstruction error, and with this step, we are able to prove our capabilities of our method. So we moved to the application of our tool inside the other challenges in development of control system. Moving back to the first CFD case, we can implement different control scenarios by rotating the cylinders inside that configuration and generating, playing with other parameters like drag and also the oscillations of the shedding. And again, here you can see that our method is perfectly distinguished between different control strategies, and it proves that we can use this method to actually somehow finding a manifold of the actuators of all of the possible actuation scenarios that is limited by some, let's say, technological limitations that we have in our problem. And using this manifold, let's say actuation manifold, as all of the possible solution to works inside the control system design. The other, let's say, ambitious step that we are doing right now is to actually bridging the gap between the field of design and optimization with our model. We all know that in our design cases we deal with different parameters, different design parameters. I don't know, maybe in your case it could be propellant, weight of the propulsion, plasma propulsion, and also don't know the currency in the tether satellite or anything. But the thing is that the output of our method, the dimensions that we can obtain, not necessarily guarantee a correlation between these dimensions and design parameters. So we have to develop another link, which is, we call it a predictor, to actually somehow translate these design parameters to our low dimensional dimensions. So we applied this method, this full picture tool, into the case of design of the aircraft wing. And here you can see that we consider different flow conditions, flight conditions with different Mach and alpha. And on the right-hand side, here we have this gamma 1 or gamma 2 or first low dimensional dimensions. And by using our tool and comparing with other actually works that has been done recently using different types of decoder and different types of predictors, we can show that our method was quite successful in following the actual behavior of the system, especially to capture the shock wave in the CT distribution on the wing. And also, if we consider the errors between the actual pressure distribution and also the reconstruction pressure distribution, we can say that among all of the different decoders and also predictors, our method were successful in actually most of the, actually in all of the different flight conditions. And yeah, it is quite successful to reconstruct the pressure distribution. Things that we are going to do is to expand our analysis of the manifold, actuation manifold, and relate it to the control system design problem. And also we have to pose some more challenges to or than the last case study to face with different flight conditions. Of course, in this last year, I have this, let's say, right task to add to our contribution that we have already done in scientific journals and conferences. And at the end, I would like to thank Comunidad de Madrid and our university, who has jointly funded our work. And thank you very much for your attention. And if you have any question or any recommendation, it is the time. Thank you.